This video deals with wave interactions and dealing with constructive and destructive interference and how those interferences can create a standing wave inside of a medium.
All right, a couple wave behaviors we're going to talk about is the superpositioning of waves. When waves interact with each other, they actually pass through each other as if they're not even there. With objects, with tennis balls, for example, when two tennis balls meet, they bounce off of each other. But waves don't do that. They pass through each other.
In talking about constructive and destructive interference, we're going to use this simulation here. It's a PhET simulation that uses a wave on a string. So we're going to actually send a pulse through this wave, and you can see that wave as it transfers back and forth across the string. All right, so one thing to notice is that this end over here with a clamp is a fixed end. And what that fixed end means is that it means it won't vibrate up and down as the wave hits it. So to give you what conversely looks like a loose end, and you can see the loose end is allowed to vibrate up and down as the wave hits it. Now, one thing I want you to notice, the difference between a fixed end and a loose end. A fixed end, when the wave reflects off of the end, a fixed end will invert the wave. And you can see it on this side as well, where the wave, when it hits, will come up, and then on the other side, the wave goes down. On a loose end, as the wave hits it and reflects, the wave will actually stay on the same side of the equilibrium. So this line represents the equilibrium, and you see the wave is above, and when it hits, it's above still.
So what happens if you have two waves that are on the same side as the rest position? So we have a crest here and a crest here that are both moving toward each other. And this is the same as a trough. If you look at this upside down, basically you got a trough and a trough that would be moving toward each other. So what's going to happen here? As the two waves meet, they actually add to each other, which is called constructive interference. And as they pass through each other, you can see that the wave, this one moving to the left, is going to pass right on through and just keep moving to the left. This one moving to the right is going to just keep on passing on and moving to the right. And when they're meeting at that moment in time, they're going to add to each other, but when they separate, they move on as if they didn't even interact with each other.
So we got this wave that's going back and forth, and what I'm going to do is I'm going to create another wave and let the two interact with each other. So when that hits, you see the two waves. When they're on the same side of the equilibrium position, they actually add to each other. When they're on opposite sides, they're going to take away from each other. So I'm going to pause it right here, and you see the two waves as they come in. I'm going to take it one step at a time, and you can see that each wave, when they add together, they give a bigger wave. So that bigger wave has a bigger amplitude because when two waves constructively interfere, meaning they're on the same side of the equilibrium position, that orange line, by the way, represents the equilibrium position. When they're on the same side, they add to each other. So their amplitudes are going to add to each other to give a bigger amplitude. Now, as the wave keeps moving, you see that the waves are going to go through each other, and then afterwards, the waves are the same waves that were passing through. And as they pass through, they just continue on just as they were going before, as if they didn't even interact with each other in the first place.
The next part, let's suppose they're on opposite sides of each other. We got a crest and a trough, and this is not just transverse waves, longitudinal waves. Let's say you get a compression and a rarefaction that meet. Well, what's going to happen is destructive interference. Since they're on opposite sides, they're actually going to take away, they're going to subtract from each other for just that moment in time until they pass completely through each other, and they're going to move on as they were before, as if they didn't even meet.
All right, so when we look at them, when they're on the opposite sides of the equilibrium position, you see there's a trough over here and a crest over there. And as they start interacting with each other, you can see that when they have the same amplitude, they will actually destructively interfere. And they give almost a flat line. So what does it look like when I have actually two different waves of different heights? Okay, so we're going to send one wave on, and then we're going to change the height of our second wave and allow it to go back and forth as well. All right, so our second wave, you can see the two with a smaller one. When they constructively interfere, they still add to each other. When they destructively interfere, they take away. So you see the two amplitudes. When I add them, I still get a bigger amplitude, so they add together still. And then when they destructively interfere, you can see that they still take away from each other, but when they're on top of each other, I still have a trough. Now you'll notice that the trough the wave that was coming in on the right here had a bigger amplitude. It was further below than the one that was above the amplitude, the crest. So when they meet, there's actually still a trough, but it's less of a trough than it was before. All right, so we've got constructive and destructive interference.
All right, standing waves is a continuous wave that has points of no movement, which is called a node, and a point of maximum movement, which is called an antinode. So basically what you see, for example, with a slinky, you're going to see a vibration of the slinky. You're going to see one part moving up and down a lot, and then one part that's not moving up and down at all. This is going to be a combination of reflections and interference. So basically what happens is we're sending a wave down this way, and when it reflects, it comes back this way and interferes with itself. So as it passes through, we get this standing wave where we get crest that becomes a trough, and then a crest becomes a trough, back and forth, back and forth. Now if you notice, we get a point right here where we have no movement up or down. That's called a node. And then the points right here where we have maximum movement, that's called an antinode as it vibrates back and forth.
So with constructive and destructive interference, we get what this phenomenon is called a standing wave. All right, so a standing wave, what it is it's basically a wave that goes to one end, reflects, and then comes back, but then it's oscillating. So it's not a pulse wave, it's an oscillating wave. And you can see as the wave goes down and reflects back, it comes back the other direction, and there's still oscillations going on. So what happens is the wave that bounces back starts interfering with itself, starts creating constructive and destructive interference. And since it's an oscillating wave, meaning it's continuing to go and keep going the entire time, then that means the wave continues to be produced and it continues to be oscillating with itself. All right, so you'll notice at this end over here that we have a part that is not moving up and down. That part of the standing wave we call a node. And then this part over here, I know it's going up and down, but it's not going up and down very much. That's actually going to be another node because it is not adding any more energy to the system. Okay, so let's go ahead and make that a node and see as it oscillates up and down. So we have points over here where we have no motion on each end, and then in the middle we have a maximum displacement. This maximum displacement is referred to as an antinode. An antinode. So nodes are points where you have no displacement up and down as the wave keeps reflecting back and forth, and then antinodes is where you have maximum displacement. Now looking at this, how much of a wave do you see? So we'll pause it, and what you can see here is that it's only a crest. And since it's only a crest, that means it's half a wave, because a full wave includes a crest and a trough. So this being half a wave from node to node is 1/2 of a wave. That means from node to antinode is 1/4 of a wave. So whenever you see a standing wave, from node to antinode, it's always going to be 1/4 of a wave. So let's redo this, and instead of having a frequency of 0.25, let's increase the frequency to double that frequency. So the frequency is going to be 0.5, and we'll let it start oscillating again, and then create its standing wave. So as it oscillates back and forth, you see the wave reflect on itself and come back in the other direction. Now, as it starts oscillating, you'll actually start seeing some of those nodes and antinodes that are produced. And once we get a good oscillation going, we'll go ahead and take the amplitude down to 0 so no more energy is put into the system. And you see this standing wave going back and forth. Okay, now this standing wave, you can see there's a node at this end, a node in the middle, and a node at the end over here. And then this is an antinode, and this is an antinode. So you see that there are 3 nodes, there are 2 antinodes, and so the question is, how much of a wave is this? How much of a wave is this? So let's go ahead and pause it. And we see that the wave has a trough and a crest. So this is one full wave. Now, if I'm looking at the wave itself, as it goes back and forth, I can count from node to antinode. That's 1, and then 2, 3, 4. So that's 4 parts of a standing wave. And remember, from node to antinode is 1/4 of a wave. So 4/4 of a wave is one full wave. So this is one full wave as we go across. All right, so now let's really take it up. Let's go to 1.5 hertz. So that's all right. So 1.5 hertz, we'll send it oscillating. We'll give it some amplitude. All right. So now we see that we have a node here, an antinode, a node. All right, so we got all of our nodes and antinodes identified. So let's start talking about how many waves that are here. Okay, so ignore the wave for a second, just talk about nodes and antinodes. So from this node to this antinode, that's going to be 1, to the next node is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12 parts from node to antinode, and 12, remember each one is 1/4, so 12/4, that gives me 3 waves. All right, so as this is going, let's go ahead and pause it. So we have a trough and a crest, trough and a crest. So the trough and the crest, that's 1 wave, and then 2 waves, and then 3 waves. Okay, so remember, from node to antinode is 1/4 of a wave, and 12/4 gave me 3 waves, and you can see those 3 waves there. Now, so with this wave, what we see is we see it starting on the left-hand side and then the wave obviously moving to the right. All right, so as you see the wave moving over, what we're going to do is we're actually going to, it's going to reflect off of the side here, and that's what the orange wave is for. We just look at the orange wave, you can see the orange wave as it comes through, it's bouncing back and basically reflects, the blue wave reflects off of the right-hand side, and then the orange wave is what comes over to the left. So these two together, what they do is the blue wave is moving to the right, and then the orange wave is the reflection that's moving to the left. And you see the two are actually going to be interfering with each other. Now the green wave that we have shows what happens with that interference. Now with that interference, you see that we're going to have a node, and in the middle we have another node, and on the end we have another node. Now again, the blue and the orange waves show what's happening as the wave moves to the right and then reflects and moves to the left. So let's kind of hide those right now. And this is the result of what we see with the green wave, as the green wave is the standing wave as the waves bounce back and forth. All right, so what we see is we see a node, that's 3 nodes, and then we see these antinodes here as well. So if you notice, let me go ahead and pause this. And as it's paused, you see that it's one full wave as it goes through. So we're going to go real time. Actually, we're going to do fast, a little bit fast, so you can see what happens here. So with the node to antinode, that's 1/4 of a wave. And then that antinode to node is another 4th. And then to the antinode is another 4th. And the antinode, or to the node, is another 4th. So that's 4/4 of a wave, which is 1 full wave. And with that, you can see that full wave there. So with doubling the frequency, we get to about 0.42. I couldn't get exactly a 0.42, but you still see the standing wave here. All right, so let's hide the green wave and look at the blue wave. And you see the waves as it goes to the right, and then the orange waves as the reflection as it comes back to the left. Both of those together. You see a little bit of oscillation between those. Now the green wave, you can see that it oscillates with it. All right, so as we go through, as the waves reflect back and forth, I'm going to pause it. And you'll notice when the waves line up, so the orange wave again is the wave that's moving to the right, moving to the left, and the blue wave's moving to the right. And when they line up, you get an amplitude that's twice as much because they add to each other. And then you have the waves, the 2 troughs that add together to give the bigger wave down the bottom as well. All right, so here you see that the crest of the blue wave and the trough of the orange wave are lined up. And with those lined up, you see that it's going to be flat. And then you see that basically when the blue line is up, the orange line is down, and it gives almost a perfectly flat line. And that's what happens with this. You got destructive interference, and then at other times you have constructive interference where they add to each other. And that gives us our standing wave.